Hello everyone. In today's video, we are going to talk about the gradient descent algorithm and look at its implementation using the Python software. When we talk about the gradient descent algorithm, it is an optimization algorithm that is used in machine learning, deep learning, or artificial intelligence models to minimize the cost function by iteratively adjusting parameters in the direction of the negative gradient. The aim of this is to be able to find the optimal set of parameters. So that is the idea. So in today's video, what we will try and do is we will implement this algorithm from the scratch, and we will do that manually. And then after that, we will analyze the impact of hyperparameters, where we will specifically look at the learning rate. And then we will compare this manual implementation to the scikit-learn library using the advertising versus sales dataset. So when we talk about the advertising sales dataset, it basically has three features. Now, these three features are the spending on TV advertisement, radio advertisement, and newspaper advertisement. And then the target variable is the sales revenue obtained per combination of the advertisements. Now, in the data pre-processing step, what we'll do is we'll try and standardize all these variables based on the z-score standardization procedure. Then after that, we predict the sales. So this is a brief mathematical foundation to the gradient descent algorithm. When we look at the gradient descent algorithm, we look at this relationship where our predicted target variable is a function of the bias and the weights times the actual variable. So when we talk about weight 1, this weight is the weight of variable x1 or feature x1. And then W2 is the weight of feature x2, and W3 is the weight of feature x3. We will use the cost function to evaluate our model. So the cost function, which is a function of our bias and weight, is the summation of the difference between our individual observations and our predicted y's squared divided by n. Then after we've had our cost function, we can now do our parameter updates. And how do we do our parameter updates? Our parameter updates are obtained by computing the gradient of the cost function with respect to the specific parameter we are thinking about. So if we are thinking about the bias parameter, then it means it is the gradient of the cost function with respect to the bias times the learning rate. And then if we are thinking about the weight of feature J, then it means it is going to be the gradient with respect to the weight of feature J times the selected learning rate or learning parameter. So when we talk about the learning rate, it determines the step size of the iterations that can be done. So with this being said, we will jump straight into our codes. So in a manual implementation, what I do is I call in the pandas and NumPy libraries. And then what I do is I import my advertisement data. So what you have to bear in mind is if you are doing this yourself, you have to change the directory of the advertisement dataset on your computer. So this is my directory on my computer. So you would have to find the directory of the advertisement dataset. So when I do that, I call it sales data frame, and I see no errors in the console. And when I come here, I see the sales data frame here. So it tells me here that I have 200 observations and I have 5 variables in there. And I can decide to print it some few observations and look at it. And so this is observation 1 to through 5, and I'm seeing spending on TV advertisement, spending on radio advertisement, spending on newspaper, and then the sales received for each combination. So what I now do in this step is I try and set my features and then my target variable. So the features are these 3 variables spending on the 3 different modes of advertisement. And then I also run or create a vector for my target variable. Then in the standardization step, recall that the Z score standardization, it is the observation minus the mean of the observation divided by the standard deviation of the observation. So that is the formula I use here. And then over here, because I have 3 variables in the matrix, this is what I use. So I create that here, and I still find no errors here, so I'm good. So then we initialize our bias and weights. And for us to initialize our bias and weights, we just randomize them. So we perform a random initialization of the bias and weight. So I set the seed here for consistency, and you can use any number you want, any number of digits you want. I'm using 37 here. And then when I initialize these, this is what I get initially. So the bias is 0.68, the weight for x1 is 0.94, the weight for x2 is 0.46, and the weight for x3 is 0.19. So these are the initial random weight of bias and the initial random values of bias and then weight. So I try to just predict my outcome or target variable based on these random bias and weight. So when I predict it and I look at the first 10 observations, this is what I find. Now take note that these were just random. So I'll try and compute the cost function for these randomized ones. And the cost function we are using is the mean square error. So once I do that, I can view the cost function, and I'm seeing that the cost function here is 0.64. So just by randomizing my initial bias and then weight, I'm seeing that the cost function is 0.64. Now, the cool thing about the gradient descent algorithm now comes in here, where I can update this bias and weight based on iterative learning. So then I write my function here in order to be able to update it. So this function now has my values of my x and y and the predicted hat, and then I also have my learning rate here. So then I begin, and then once I begin, I try and then I do the first set of updates here. And when I do the first set of updates, I say in line 94 that it should print the bias and weight after the first update so that I can see what improvements are there. And then I also in line 91, I predict after the initialization. So this is what I'm seeing. So after the initialization, this is what we got when we did it initially. So we had 0.68, 0.94, 0.46, and 0.19. Now, the first update, after the first update, we are seeing that the bias has changed to 0.66. Our weight for x1, x2, and x3 have changed slightly to 0.94, 0.4639, and then 0.189. So we can now increase the number of iterations in order to see the improvement. So I do the number of iterations as 100, and I begin with a learning rate or hyperparameter of 0.1. So once I do that, I can also view what would happen if I change my learning rate. So you see here that when I change my learning rate, what I'm seeing here is that my bias is now 0.45, and then my weights have become 0.87, 0.46, and then 0.13 for my features x1, x2, and x3 respectively. So then I can decide to just do a simple plot of how the cost function relates to my iterations. So when I run this, I come here and I check. So we are seeing that as the number of iterations increased, the cost function also declined. And this cost function, we actually want it to be small. So we see that it declines here after 175 iterations to something slightly above 0.35. Now, the question is, we want to have a very small cost function. And we are seeing from here that there is a sharp decline. Does it mean that if we increase the number of iterations to, let's say, 1,000 or 2,000, we could see further decline? We don't know. So why don't we compare the two hyperparameters and then increase the number of iterations to 2,000 and then see if we will see any particular change. So here I'm using the first alpha parameter as 0.01, and then I'm using the second alpha parameter, and the alpha parameter is the same as the learning rate or hyperparameter. So I'm using the first alpha as 0.01, and then the second alpha as 0.001, and for both of them I'm maintaining 2,000 iterations. So I run that, and then when I run it, this is what I'm seeing. That I'm seeing that for the first one now, the bias is negative 5.57. And then for their weights, we have 0.75, 0.53, and then negative 0.004. And then for the second hyperparameter, I'm seeing that the bias is 0.012, and then the weight one is similar, weight two is almost similar, but then weight three becomes positive. So then I want to plot the, because it's the cost function that we use to compare which one is performing well, right? So I want to plot the cost functions of these two hyperparameters that we've used. So I plot the cost function, and this is what I'm seeing. So what I'm seeing is that the higher learning rate, which is alpha of 0.01, shows a very fast convergence. So it drops sharply. And then when it drops sharply, there is a potential that this sharp drop could make it less stable. However, in this case, we don't have evidence that the sharp drop has made it less stable. But when we see with the lower alpha value of 0.01, we see that it takes more iterations in order for us to see convergence. However, we see some stability in the drop. But the good thing is both of them eventually converge successfully. So what we can do is we can decide to compute the mean square error, and then we see what the mean square error is. So what we see now is that for a learning rate of 0.001 based on our 2000 iterations, the final mean square error is 0.10, and that is very, very low, which is very, very good. Now, the question is, would we have had a better mean square error if we had trained this machine learning model on a least square regression instead of the gradient descent algorithm? So let's compare and then see what we get. So for us to do that, I use the circuit, and then what I do here is I split the original data into a training and a testing data. And what I choose a training of 70% and a testing of 30%. And in order to ensure reproducibility, I maintain the same random seed that I had used in the initial one. So I do run these. Okay. So once I run, at least I get a confirmation that my testing has 60 observations. And don't forget, we began with 200 observations. So 30% of 200, I think, should be 60. So that is right. Then now, I'm sure all of you are aware by now that we build our model on the training data set. Then we test the model on the testing data set. So we are running our model on our training data set, and it is the same model we are running where our features are TV, radio, and newspaper advertisement, and then the target is our sales we obtain. So when we do run, these are the coefficients we are getting for our training model. So we are seeing here that the coefficient of TV is 0.04, we have 0.19, and then we have negative 0.005. So then what we want to now do is we want to make predictions on the testing and then see what we are going to get. Because don't forget that normally if you do the predictions on your training, it gives you optimistic values. It gives you optimistic values because the model has already seen those observations. So you always want to use or test your model on your testing data set. So that is what we do here. So now we want to actually compute our model fit. So we create a data frame for the predictions from our testing, and we do have the test data frame here showing here, which has our actual data predicted and the residuals. Then we can just try and show randomly 10 observations from that data frame, and this is how it looks like. So then we want to measure the accuracy of this. So of course we can use the R squared to check that, and we run the R squared here, and then we are seeing that it is 89%, right? And 89% is normally good, right? But recall that our cost function we used in the gradient descent algorithm was the mean square error. So it's difficult to compare this R square we have here to the mean square error. So why don't we compute the mean square error from this model? And of course, you can also compute the root mean square error if you had wanted. But for comparison's sake, we compute the mean square error. Then when we compute the mean square error, we'll print it out and see how that compares to the mean square error we got from the gradient descent algorithm. So we see here. So we are seeing that the mean square error from the machine learning model based on the linear or the least squares method is 2.35, and that from our gradient descent algorithm is 0.10. And because when we talk about mean square errors, we want the lower one to be bigger, we see that our mean square error for the gradient descent algorithm performs far better than that from this model. So this is a nice introduction to the gradient descent algorithm, and we see how it performs better than the least square regression model. I hope you enjoyed this. Thank you.